Hey everyone, welcome back. So last time, we were starting to look at molecules that had two atoms in them, and seeing what happens to the polarity of the molecule. Does it take a positive or negative charge? Does it stay neutral? What's going on when we have electrons being pulled in either direction? So just let me just recap for that. I have here, if I have two H's, so there's electrons in the middle, and if I have two H's, they have the same electronegativity, and so if I pull on the electrons, they pull evenly, and so the electrons are right in the middle. They're not pulled in either direction, and we say that this is non-polar. It does not have a positive or negative side to it. It doesn't have like a north pole and a south pole. It's just um, pretty much neutral. They're evenly shared electrons. So they are right in the middle. Now, if I take one of these atoms and I change it now to something more electronegative, let's say chlorine. So I'm going to take this and change it to chlorine. And now let's see what happens. So chlorine has a much higher electronegativity, and when they start pulling on the electrons, now the electrons get pulled towards the chlorine a lot stronger than they do with the hydrogen. So electrons, remember, are negative charge, and now the electrons are way over here by the chlorine. So that means this side of the molecule takes on a negative charge, whereas this side is now partially positive because you have to balance it out. So that makes a polar molecule because it's got two poles on it. It's got a positive pole and a negative pole, and so it's kind of like the North Pole and the South Pole. Now this molecule is polar and it's got some charges to work with. So now, instead of looking at just molecules with two atoms, we're going to start looking back at water and something a lot bigger like oil and seeing what's going on with those molecules. Anyways, back to this here. So this is water. Water has a three atoms in it, and oxygen has a electronegativity of 3.44. Hydrogen's got 2.20, and this hydrogen here's got 2.20. And so the last activity we looked at, or two activities ago, we looked at what's going on with the electrons in this molecule, and some people were a little confused, and so I want to kind of go over that. So we have two bonds here. We'll talk more about bonds next week, but a bond here is basically two electrons that are being shared between these two atoms here, also right here. And as the electronegativity of oxygen is much higher, the electrons get shifted in this direction. So now we've moved from here to here. The electrons are now pulled toward the oxygen. As you can imagine, with this much pull towards the O, now this becomes partially negative. So electrons are negative, and as we saw with the rubber band thing, when electrons get pulled in one direction, that causes that side of the molecule to take a negative charge. So in here, hydrogen now takes a positive charge, and then for the activity, you're also going to have a couple of water molecules to organize, and you can take them, and I say you can move them around like this. You can rotate them, and so I need you to take them and move, rearrange them and organize them in a way that the poles are going to be attracted to each other in the right direction. Remember what attracts what. We don't want couple of things repelling each other, and then you're going to move these things around. You can move them, you can change the direction of them, so you got to move them and make the attractions, show a couple of attractions of these water molecules and explain why you did that. Okay, so do I want, for instance, an attraction like this? Is an H going to attract an H, or is an H going to attract an O? How is that going to happen? Moving around and see how am I going to get this set up like that. Okay, the next molecule was oil. So oil is a giant molecule. It's got actually lots of molecules in it, but this has got lots of C's and H's. So a lot of people point out that we do have lots of C's and H's. A couple O's down here, but mostly just tons of carbons and hydrogens. And so now we got to figure out, well, what's going on with the electrons here? And so if I were to start drawing electrons in here, each of these lines actually is a bond. And so I would have some electrons here. I would have electrons here, electrons here. I would have electrons here, and everywhere. So I would be drawing electrons everywhere. There's so many electrons here, there's no way I can kind of take care of this. And so, move this out of the way so you can see this. And so the question is, well, if I have hydrogen has electronegativity of 2.10 or 2.20, excuse me, and carbon is 2.55, well then, what's going on? Why is this molecule nonpolar? So think about what's going on with the electrons here. Are they being pulled in any direction, really? And if they're not, then this whole thing here, remember, if I subtract these two numbers, if it's less than 0.5, then they're not really pulled in any direction. So why does that make it nonpolar? And then, if you recall in the last activity, we looked at that nonpolar and polar interactions, and we know, well, oil still has some interactions. It's a liquid, right? We have it as a liquid at room temperature, and so it has to stick together. You have to have attractions in order to be a liquid. You have to have attractions in order to be a solid. And so oil has got some attractions. Do you think they're as strong or not as strong as polar attractions? Okay, so finally, we're going to start moving back into this idea that what's going on with polar and nonpolar things. So polar things like water, we have plus and minus charges, and the thing that we got to know today is our phrase is like attracts like. So polar things like polar things. Polar, this is attraction here. This is an attraction here. This is an attraction here. This is an attraction here, and so on. So there's attractions everywhere here, and positives and negatives like each other. Likewise, nonpolar things like nonpolar things. So this is all nonpolar. They want to be by each other. So they're fairly neutral. All the neutral things want to be near each other. However, we also found out that polar things do not like nonpolar things. So we see here, water's at the bottom, oil's at the top. They don't like each other. They don't want to be near each other. And so I want to show you, this idea that polar things like polar things. How can we show that? So let me stop the video here for a second. We're going to go to an experiment, and we'll be right back. Okay, so the first experiment we have is really short, but it's about mixing things. And I really want you to think about the idea of mixing as being an interaction with another substance. So I have a little cup of water. That's all you need. And I'm going to mix, so we know water is polar. And we are going to mix some different kind of polar substance into the water. And remember, mixing, interacting. Why does something interact with another thing? Why does one polar thing interact with another polar thing? So this is just some rubbing alcohol. Rubbing alcohol is not as polar as water, but it is polar. And so if I take rubbing alcohol and I take some and I pour it into the water, we can see there's some wavy lines or something, right? But in general, it is like it mixes in there. You don't see another layer. It's all one continuous thing. So it's one solution. It is interacting with the water. So one polar substance will interact with another polar substance. But if I go back to my nonpolar substance, I don't have any other nonpolar substances at home. But we go back to our standard oil, which is nonpolar, and I pour that in here. Well, we can see it does not interact. Okay, so why doesn't a nonpolar substance interact with a polar substance? Always think about charges. Why? What do I need for something to interact with something else? So our final part of this lesson is looking at how soap and sanitizer work, and what is it doing when it's interacting with water and with oil. So remember, mixing is interacting. And so this is soap. Soap it's kind of a unique substance. It's got, when we think of things as mostly being polar or mostly being nonpolar, but soap actually, when they designed it, it's got both parts of it. This has got one side of it is what we call polar. So this is the polar head of soap. And this, way down here, all this stuff, lots of C's and H's. So we talked about C's and H's, and that's nonpolar. So we know now sanitizer is also kind of built the same way. It's got one side of it is polar, but this side here, the nonpolar side, the C's and H's, like what do we notice about these substances? So it's a short experiment here. You're going to take a little bit of sanitizer and a little bit of soap and put them into oil and put them into water and see how do they interact with those things. What we're going to do is you're going to need a couple containers. I have a couple cups with water in them, and I have a couple of little cups. These are just medicine cups, but if you have any kind of dish or whatever, just a little bit of oil in these. We're going to take a look and see what hand sanitizer, how do they interact with the different substances. So sanitizer and soap. We're going to try the soap first. So I just have some dish soap. Take a little bit of dish soap. That's a giant container, but I'm going to go ahead and put a little bit in here. So this is the water. Put some water into the dish soap. So you can see at first, the dish soap is like that, but if I just go ahead and take you need some toothpicks or a spoon or something, and I stir this up, eventually the soap will totally mix in with the water. And if I just kept stirring that, it'll totally get into there. So you're not going to see a separate layer. If I take soap and I put it into oil, so this is the oil, a little bit of soap and oil. Okay, so initially you can see I got some bubbles floating around here, so you guys can see the oil in there. So you can see a layer, but if I mix this in, it gets a little cloudy, but eventually it mixes in there pretty good, okay? So soap and oil, it will mix in there, okay? It's a little cloudy, but it does interact with the oil. Now let's try the sanitizer. So sanitizer, take sanitizer, put it in the water. Okay, so you can see initially there is a separate layer. You can see some, it's hard to see. So you can see a separate layer right there. But if I mix it up, so that mixes in pretty good. All right, so the sanitizer does mix in with the water, so that's interacting with the water. Now let's try the sanitizer in the oil. Okay, so initially you can see also a separate bubble. There's another layer in there. It's not the soap really kind of mixes in there quite well. The sanitizer just kind of stays as a bubble here. And if I mix this, you see that? Let me get this set. So it's just staying at the top there, right? That is kind of a separate layer. So you can see a separate layer still. It's not mixing quite as well. And that's kind of the big question, is why doesn't the sanitizer interact with the oil as well as the soap? This is the soap. Okay, so it's really kind of getting in there. It is all throughout the solution, all throughout the oil. The sanitizer not really mixing in as well. So why is that? Looking at the structure of the molecules, why doesn't the sanitizer mix as well? Okay, so we're back now. And so I want to talk about, what did you notice about how the soap and sanitizer interacted with the water and oil? Did one interact better than the other with water or with oil? And then think about why that is. So the first thing is interacting with water. So as they interact with water, which is polar, what do I need for each substance to interact with water? Well, it needs to have something polar in it. So soap has got this polar side here. Sanitizer also has this polar side. What do you notice about how big these sides have to be in order for them to interact? Does the polar side really need to be really big or small? What do I notice about when I compare these two polar sides with each other? So that's the first thing. Are they really a whole lot different? There's another O here, but really, is it a whole lot different? It doesn't really look like that. And so the second thing is now we're looking at how they compare with oil. So when each substance is put into oil, how do they interact? Soap, we got this giant thing here, so we need something non-polar to interact with the oil. And soap has this thing. Sanitizer has this part. What are the differences here? Why does one interact a whole lot better than the other in oil? So give that some thought, kind of write about that, and I will see you next time.